A great white shark, believed to be the largest in North America, has been spotted off the coast of Nova Scotia, weighing more than 3,500 pounds.
Imagine this for a moment. A 9-foot great white shark, one of the ocean's most efficient predators, suddenly vanishing into the jaws of a predator. Sounds impossible, doesn't it? Except this is exactly what happened. In the unpredictable world of the deep blue, predators lurk unseen, each ready for the kill. But how gargantuan would a killer have to be to take on a great white? This is exactly what came to light when scientists finally discovered the predator that swallowed a great white shark whole. The final moments of a female shark. In 2003, off the remote southwestern coast of Western Australia, researchers from the Commonwealth Scientific and Industrial Research Organisation, or CSIRO, attached a pop-up satellite archival tag to a healthy female great white shark measuring approximately 2.7 meters or 9 feet. The project was part of an effort to map the movements, diving behavior, and migration corridors of one of the ocean's most elusive apex predators. At the time, great white sharks were still poorly understood in terms of deep diving behavior, long-range travel, and survival patterns across the Indian and Southern Oceans. The device itself was not a tracking beacon in the traditional sense. It was a self-contained environmental recorder known as a PAT, or Pop-up Archival Transmitting Tag. Once attached, it quietly logged depth, ambient temperature, and light levels at fixed intervals, storing months of data internally. After a programmed duration, typically several months, the tag would detach, float to the surface, and transmit its stored information via satellite. This delay meant scientists often waited long after the animal had moved on or died to reconstruct its final movements. For this particular shark, the data arrived months later when the tag washed ashore near Bremer Bay, roughly 500 kilometers southeast of Perth. The recovery was routine at first. Researchers expected a standard migration profile across temperate waters. Instead, what they downloaded defied that expectation almost immediately. For most of the record, the shark behaved normally, diving between surface waters and deeper cold layers, consistent with known great white hunting patterns. Then, suddenly, the dataset changed character entirely. At one precise moment, the recorded ambient temperature spiked from approximately 8 degrees Celsius or 46 degrees Fahrenheit, typical of deep Southern Ocean waters, to around 25 degrees Celsius or 78 degrees Fahrenheit. This was not a gradual shift or seasonal fluctuation. It was abrupt, sustained, and biologically significant. In marine environments, such a rapid increase does not occur through movement between water layers alone. It implies a transition into a thermally stable internal environment, something alive and warm. Almost simultaneously, the depth data showed a dramatic descent. The tag dropped rapidly to around 580 meters, or about 1,900 feet, far deeper than the shark's prior movement pattern during the recording period. The rate of descent and the stabilization at depth did not resemble the typical free-swimming behavior of a great white. Instead, it suggested the shark, and the tag attached to it, had been consumed by a much larger organism swimming through deep water. For several hours, the temperature reading remained steady at approximately 25 degrees Celsius. That consistency is critical. In oceanographic terms, the surrounding seawater at those depths would have been close to 7 to 8 degrees Celsius. The only plausible explanation for a sustained, warm microenvironment of that magnitude is the interior of a large endothermic animal. The tag was no longer recording open water conditions. It was recording conditions inside a body cavity where digestion could occur. Eventually, the data showed a gradual return toward cooler temperatures. The tag was expelled and later drifted to the surface, where its programmed release mechanism activated. From there, it transmitted its archived record to the Argos satellite network, where CSIRO scientists finally reconstructed the timeline. What they were left with was a sequence that suggested a catastrophic encounter. A healthy, juvenile to subadult female great white shark had been consumed whole or nearly whole by another predator. No bite marks, no visual observation, no direct witness, only temperature curves, depth spikes, and timing data. The identity of the predator was not captured in the record, but the implications were immediate and unsettling. The ocean's most iconic apex predator had, for at least one moment, become prey. The hunt for the unknown predator. The first serious suspect was the orca. Killer whales, Orchinus orca, are among the few confirmed predators of great white sharks, with well-documented cases off South Africa. By 2017, at Gansby, 2 male orcas, nicknamed Port and Starboard, were observed killing multiple great whites and selectively removing their livers, a nutrient-dense organ that can constitute a large portion of a shark's energy reserves. At first glance, this made orcas a compelling candidate for the CSIRO event, but the physics of the tag data did not cooperate. Orcas are mammals with stable internal body temperatures around 36 to 37 degrees Celsius. The recovered tag, however, recorded a plateau near 25 degrees Celsius, far too cool for a marine mammal digestive system. Attention then shifted toward less familiar predators, giant squid, sleeper sharks, and other deep-sea mesopelagic species. At first glance, these animals sit in the right part of the ocean, dark, deep, and rarely observed. Here, unusual encounters feel plausible simply because human visibility drops sharply beyond a few hundred meters. But once researchers tried to match behavior to mechanism, the hypothesis started to fracture under its own biology. Take giant squid first, including species such as Architeuthis ducks. These are formidable ambush predators capable of taking large fish and even deep-diving whales in rare cases, using long tentacles lined with suctioned hooks to seize prey in near-total darkness. But their hunting strategy depends on rapid strike and external processing, not internal consumption. Even if a squid had seized a shark of that size, already a stretch given relative mass and escape dynamics, it would not produce a sustained internal temperature of 25 degrees Celsius inside a sealed digestive environment. Squid are ectothermic. Their body temperature simply mirrors the surrounding water, meaning the tag would have remained near deep ocean baseline values around 4 to 8 degrees Celsius. The thermal signature alone eliminates them. Sleeper sharks, particularly members of the genus Somniosus microcephalus and related deep-water species, present a more interesting case. These animals are slow, energy-efficient ambush predators that can reach impressive sizes and are known to scavenge or opportunistically feed on fish, seals, and carrion. In theory, a large sleeper shark could consume another shark, especially if the target was weakened or already compromised. However, their hunting mechanics are incompatible with the observed data sequence. They are not fast vertical divers. A rapid descent to 580 meters immediately after ingestion would not match their low metabolism, slow-motion locomotion style. More critically, their internal temperatures track closely with ambient deep water, typically near 0 to 7 degrees Celsius. That, again, breaks the temperature profile completely. Even if one stretches plausibility further and imagines a deep-sea predator large enough to consume a great white, the behavioral constraints remain unforgiving. The CSIRO tag data implies continuous metabolic heat and active digestion at elevated temperature, something only high-performance endothermic or regionally endothermic fish can maintain. This eliminates both squids and sleeper sharks. Deep-sea predators are either large but slow and cold, like sleeper sharks, or active but physiologically constrained, like most mesopelagic hunters that rely on quick ambush rather than sustained high-energy pursuit. None of them combine the 3 conditions the CSIRO tag implies at once: rapid vertical movement to nearly 580 meters, whole prey ingestion of a multi-meter shark, and a prolonged internal environment held near 25 degrees Celsius. In ocean biology, that combination effectively narrows the field to a very small group of large lamnid sharks, where regional endothermy allows elevated internal temperatures and high-speed hunting in cold water. The most sensational alternative, surviving megalodon, emerged quickly in popular discussion precisely because it bypasses those constraints through scale alone. At estimated lengths of 15 to 20 meters, megalodon could easily engulf a 2.7-meter shark without difficulty. While it went extinct 3.6 million years ago, it is often compared incorrectly to living fossils like the coelacanth. The rediscovery of the coelacanth in 1938 is frequently invoked in these debates, but the comparison breaks down at every biologically relevant level. The coelacanth was never considered a large, ecosystem-shaping apex predator with global ecological impact. It was a deep-water lobe-finned fish, already adapted to low visibility, low energy environments. Its rediscovery in South Africa and later identification of a second population in Indonesia involved an animal occupying a stable, low-competition niche that required minimal ecological footprint to persist undetected. Crucially, it does not generate a strong fossil signal of ongoing ecosystem pressure. Megalodon, by contrast, was an apex macro-predator operating at the top of marine food webs. A species of that scale would require continuous high-volume prey intake, primarily large marine mammals such as whales and sizable dolphins. Unlike small, cryptic deep-sea fish, a 15 to 20-meter shark leaves ecological signatures wherever it exists. Bite marks on whale populations, carcass patterns on the seafloor, tooth deposition in sediments, and a measurable impact on prey population dynamics. Sharks also continuously shed teeth throughout their lives, meaning even a small population would leave an ongoing geological record. Modern marine surveys, including deep-sea dredging, coastal sediment analysis, and extensive whale fall monitoring programs, have found no such signature. No fresh megalodon teeth in recent strata, no consistent unexplained predation patterns on whales, and no biomass imbalance consistent with a hidden global apex predator of that scale. Even in the most undersampled regions of the ocean, apex predators leave disproportionate ecological traces because energy transfer at that level is not invisible. As these alternatives weakened, one explanation remained structurally consistent: the cannibal beneath the waves. The simplest explanation that survived the CSIRO tag dataset was also the most unsettling. Not a monster from deep time, not an unknown leviathan, but a much larger great white shark turning on its own kind. The data fit that model with uncomfortable precision. The sudden jump from roughly 8 degrees Celsius ambient water to about 25 degrees Celsius aligns with a transition into the digestive tract of a large regionally endothermic fish. Great white sharks, Carcharodon carcharias, are among the few sharks capable of elevating internal muscle and organ temperatures through countercurrent heat exchange systems. This allows them to hunt in colder waters while maintaining metabolic efficiency. A sustained 25 degrees Celsius reading is high, but still within the upper physiological envelope of a large active individual, far more consistent with a lamelid shark than with a marine mammal or invertebrate predator. The dive profile strengthens that interpretation. The tag recorded a rapid descent to approximately 580 meters, or 1,900 feet, followed by a period of stability. Great whites are not surface-bound hunters. Tagging programs in the Atlantic, Pacific, and Indian Oceans have repeatedly shown them diving to depth exceeding 1,000 meters in some cases. These deep excursions are thought to relate to foraging, navigation, or thermal regulation. A large shark swallowing another shark would plausibly descend during or after feeding, either to stabilize buoyancy or move into deeper, colder water during digestion cycles. From these parameters, researchers inferred size indirectly rather than directly. A predator capable of engulfing or fully consuming a 2.7-meter female would need to be substantially larger. Estimates commonly converge around 5 to 6 meters or 16 to 20 feet. That range aligns with verified large females observed in multiple regions. Individuals such as those documented off Guadalupe Island in Mexico demonstrate that great whites can reach extreme sizes without crossing into fictional dimensions. At that scale, the size gap between predator and prey becomes sufficient to enable whole or near-whole ingestion events. When apex predators become prey. The CSIRO Great White Tag case shows us that an apex predator can still become prey when a larger member of its own species enters the same unseen space. This kind of internal hierarchy is not unique to shark. Across terrestrial ecosystems, apex predators routinely kill each other when size, territory, or opportunity align. Male lions in the Serengeti frequently kill rival males during territorial takeovers. Among tigers in India's Bandhavgarh and Ranthambore reserves, territorial disputes often end in fatal encounters, with larger males eliminating smaller competitors to control breeding access. Even crocodilians in Australia's Northern Territory exhibit cannibalistic behavior, with larger individuals preying on juveniles and occasionally subadults. Polar bears in Arctic regions have also been recorded killing and consuming other polar bears, especially under food scarcity conditions tied to sea ice decline. In the ocean, this pattern becomes less visible, but no less real. The deeper researchers look into pelagic ecosystems, the more they find that apex predator is not a fixed rank, but a conditional state shaped by size, opportunity, and proximity. Great white sharks sit at the center of this paradox. Juvenile cannibalism is already well documented in the species, along with intrauterine predation in related lamniform sharks, but the CSIRO tag data points to a more uncomfortable extension of the same principle, one that does not stop at juveniles. It suggests that, under the right conditions, adulthood does not grant immunity. It only shifts where the threshold of vulnerability lies. To understand that threshold, researchers often step away from averages and focus on verified extremes, outliers that define what the species is physically capable of rather than what is typical. One of the most widely cited examples is a female great white known as Deep Blue, filmed off Guadalupe Island, Mexico, first in 2013 and later during additional encounters. She is estimated at approximately 6.1 meters or 20 feet, placing her among the largest reliably documented individuals. Importantly, this estimate is based on visual comparison with cage divers and calibrated photogrammetry techniques, not anecdotal scaling from historical reports. Across tagging programs and field studies in the Atlantic, Pacific, and Indian Oceans, most mature female great whites fall within a narrower band, roughly 4.5 to 5.5 meters. Individuals exceeding 6 meters exist, but they become exponentially rarer at each increment of size. This is not accidental. Growth in great whites slows dramatically after sexual maturity, with energy increasingly diverted into maintenance metabolism and reproduction rather than linear size increase. Prey availability also plays a limiting role. Caloric intake in marine environments is uneven, and sustained access to high-energy prey like seals or large fish does not consistently support indefinite growth. Historical records complicate this picture, but not in a scientifically reliable way. Maritime literature and early expedition accounts frequently describe 25 to 30-foot great whites, sometimes based on partial sightings, deck measurements, or retrospective estimation from damaged carcasses. Modern marine biology treats these figures cautiously, not because large sharks are impossible, but because measurement error in pre-standardized observation methods is well documented. When recalibrated using modern techniques such as laser photogrammetry, stereo diver imaging, and electronic tagging data, most of these extreme claims regress significantly toward the known biological range. Even at the upper verified limits, however, size differentials within the species become ecologically decisive. A 6-meter female great white does not just outweigh a 2.7-meter subadult. It surpasses it by several multiples in total mass, bite force potential, and energetic storage capacity. In sharks, this matters because a large fraction of stored energy is concentrated in the liver, a lipid-rich organ that can function as both a fuel reserve and a high-calorie target. Intraspecies predation, therefore, is not simply aggression, it is energetically efficient feeding when opportunity aligns. This is where the ecological hierarchy becomes visible in practical terms. A 9-foot great white may function as an apex predator within its local food web, capable of dominating seals, sea lions, and most mid-sized fish species. Yet that dominance is not absolute. It is spatial and relative. At depth, or in regions where size classes overlap, a significantly larger conspecific can invert that relationship instantly. The same anatomical design that makes great whites efficient predators, streamlined bodies, high-speed bursts, and powerful jaws scales upward into a mechanism where one member of the species can treat another not as competition, but as viable prey. What makes this dynamic particularly striking is how rarely it is observed. Humans observe only a fraction of oceanic life directly. Less than 5% of the global ocean has been visually surveyed in any meaningful resolution, and most deep-sea ecosystems remain functionally unobserved outside of remote sensing and intermittent submersible missions. Even in relatively well-studied regions, like the continental shelf of Australia, tagged animals routinely travel through areas with no acoustic receivers, no cameras, and no human monitoring. That observational gap leads to a structural problem in marine science. Rare events are often invisible, not absent. A predation event involving large pelagic sharks could occur hundreds or thousands of times across global populations without ever being directly recorded. The CSIRO dataset is notable not because the event is unique, but because it was partially captured at all. This raises several unresolved questions that continue to interest shark biologists. First, how common is adult great white cannibalism? Juvenile cannibalism is well documented, but adult-on-adult predation remains difficult to quantify due to the rarity of tagged interactions between large individuals. Second, what proportion of natural mortality in great white populations is driven by larger conspecifics? Traditional models focus on fisheries bycatch, disease, and environmental factors, but intraspecies predation is increasingly considered a potential missing variable. Third, how many similar events occur completely undetected each year simply because no monitoring device is present at the moment they happen? The CSIRO case does not resolve these questions. It exposes them. It shows that even apex predators operate within hidden hierarchies shaped by size, opportunity, and proximity, and that most of those interactions occur beyond human observation. The absence of data is not evidence of absence. It is evidence of limited coverage. Well, that's it for now. Thanks for watching. Did you like this video? If you did, please consider liking, dropping a comment, and hitting the subscribe button so that you don't miss out on our new uploads. Also, don't miss this video you see on your screen right now. It's truly unbelievable.